Hello everyone. Today in this video clip I'm going to talk about section 16.7 of our course. We're talking about surface integral. So first recall the parametric equation of surface. So the surface denoted by capital S are vector form. Okay, it's equal to x, y, z, just represent a point. So graphically this is what you have. This is my x-axis, my y-axis, my z-axis, and this is my vector r. Okay, represent a point on the surface. This is the surface S right here. Okay, so if you parameterize it, this is a review from last time. We write it r in terms of two variable u and v. It means what? X is a function of u and v. Y as a function of u and v, and then z as a function of u and v. This is my v. Okay. Oh, really, a vector r. Okay, so you have a different point x, y, z, and then you have another point on the surface. For the line, you only have one parameterized, right? It's just t, so rt, xt, yt, and zt. Then you have a line, a curve on the three-dimensional space. Two variables, you're going to have a surface. Okay, so this is the parametric equation of a surface on the space. So we define the surface integral like this. Surface integral of the function f of x, y, z, ds, integral the surface S right here. Okay, it's gonna be this. I need some room to write, so this is integral of f right here. What is x, y, z? X, y, z is really the vector r. Vector r here in terms of uv. Okay. And recall what we learned about ds. ds, last time we learned is what? The little area of the surface, right? Is RU cross RV, then time dA. Okay? So this is what we talked about last time. Right? At the point, we calculate RU, this is what? Tangent vector, direction U. This is RU times DU, and then this is RV dV, and then if you cross RU and RV, you're going to have the area of that little parallelogram times DU dV. The dA here is DU dV. Alright, so this one is ds now is magnitude of RU cross RV, and then dA. Where dA here really is du dV. And this is the definition of surface integral that we learned. So after the definition, let me just give you guys an example. All right. Let's take a look at an example in our book. See what you got. Calculate this line, surface integral. X squared ds. Well, usually we will write an s down here, I think. Right, double integral of s. Yeah, right that way. It doesn't matter to me. Okay. Calculate the integral of x squared ds. Let me see the book. Oh, this notation of s. Double integral. Okay. Of x squared ds, where S is the sphere of radius 1. So what is the surface S? X squared plus y squared plus z squared equal to 1. And this one is obviously the sphere of radius 1. And what is it? Sphere radius 1. Okay. Right. So S is the surface. That thing. Whenever you see sphere, you should think of what spherical coordinate is going to be helpful. And for spherical coordinate, I remember that x was, we translate into spherical. Let's see what we have, a point right here. This angle is called phi. Check it down here. This angle from here to here is called theta. Okay, so x was the radius. It's called rho, radius. Rho times sine phi cosine theta. Check my work. Should be right. And y is rho times sine phi sine theta. And then z was going to be rho cosine phi. That's what we have it for. But rho is 1 because the radius is 1. So we can ignore those parts. Okay. So the parametric equation for that surface is this. R of phi theta is equal to sine phi cosine theta, comma sine phi sine theta, comma cosine phi. Okay? This is going to be the parametric equation. Alright? And of course x is sine phi cosine theta. So we're going to calculate what? R phi, and we're going to calculate R theta. And we're going to cross those two, right? So what? Calculated R phi is going to be partial derivative in terms of phi. Derivative of sine is cosine, so cosine phi, cosine theta, negative cosine phi, sine theta, and then derivative of partial derivative of cosine phi is negative sine phi, I think, and then r theta is gonna be, now phi is a constant, right? Cosine of theta derivative gonna be negative sine, so negative sine phi sine theta, comma. The first, second one right here, derivative of sine is cosine, so sine phi sine theta, and then derivative of cosine phi to theta is going to be 0. Okay, now you cross them. R phi cross R theta. Okay. And how do we cross? This is I, J, K. Okay. And I think we did that before, right? Let's do it one more time. For the I term, 0 times this is 0, minus, with minus become plus. So sine square phi times sine theta, sine square phi times sine theta. That will be the first component. And then the second component is what? For the j term right here, 0 times this is 0, minus, and now the minus become plus, this times this, the middle term we change the sign, okay? So the negative times negative going to be positive. So sine square phi sine theta again. And then for the last term, jk term, this times this is going to be cosine phi sine phi cosine theta times theta. And then minus this times this is what? Sine phi cosine phi sine theta again. So let me do it quick in here. I got sine phi cosine phi as a common factor, and then we have sine theta as a common factor. Right, and then we have check my algebra. Cosine phi sine phi cosine theta sine theta sine phi sine cosine phi sine phi sine theta cosine theta, and then subtract. What do we have in here? Cosine phi sine phi, and then sine square theta. Sine square theta. All right. Now we're gonna calculate the magnitude of this. So you square this up, and then square this up, and add them up. This is we can factor this out. Got cosine phi, sine phi, and then sine out, right? So take square root. See what we got. Oh, this is a question. I should keep it. Integral of x squared ds. The magnitude of r theta cross r phi is gonna be square root. Oh, what? It's a big one, huh? This is square, so sine. Let me check my algebra. Is that right? This one cannot be the same as this one. See? Cross r phi, right? So sine is cosine, that's right. And then sine becomes cosine, right? Yeah, that's right. And then theta, cosine becomes negative sine, yeah. And then sine. Oh, this term is not right. No wonder. The derivative of sine is cosine. Check the algebra, guys. Okay, so I make a mistake right there. That last term should not be right. No wonder. And this term gonna be. Let's see. We drag a little. This one is sine for the I term right here, 0 times this, and then what? Sine phi, negative become positive, and then this is cosine. No wonder. Cannot be the same. Okay? And for the ij term, 0 right here, so this is going to be sine theta. Looks good. Because when you square, you add them up, it's going to be 0. It's going to be a very simple thing. Okay, and then for the k term, cosine phi, cosine theta, and then cosine square. Okay, cosine square theta, and this is cosine square. Oh, so the last term is what? Cosine phi times sine phi. Should be this. Okay. And now we calculate the magnitude of this. First term is what? Sine square and cosine theta squared it up. You add this one up, so it's going to be sine to the 4 phi, and then what? Cosine square theta plus sine square theta. I am square the first term up, and then square the second term up, and then I add them together. I have this, and then the last term square up is cosine square phi, not theta, times sine square phi. Okay, and this is 1 already, and then I factor out the sine square of phi. This is 1. Okay, so the first term and the last term is what? Factor out the sine square phi. I got sine square phi plus cosine square phi. And don't forget that we have square root. And again, this is 1. Sine square root is equal to sine phi. Okay, so anyway, this is R, the parametric surface of the sphere. And we have r phi cos r theta magnitude is equal to psi phi. We did it a couple times. Okay? So, apply to our problem right here for the surface integral. My x is sine phi cosine theta. So x squared is double integral right here. Sine square phi cosine square theta, ds is sine theta and times dA. Now, since this is spherical coordinate, I have to convert this into spherical coordinate. So what? dA is dr d theta, right? Yes, that's right. dA here is d phi and d theta. And for the spherical coordinate, going to draw it one more time. This is phi going to run from 0 to 180 degrees, all the way from here, all the way down here. Okay? And then theta runs from 0 to 2 pi. We'll check it down here, and this is the angle theta. Entire circle on the xy plane. Okay? So this double integral now got a boundary theta right here run from 0 to 2 pi, and phi run from 0 to pi. Okay. Is this separable? Yes, it's phi and theta. It's integral from 0 to 2 pi of cosine square theta times the integral from 0 to pi cosine square times another sine is going to be sine cube of phi. This is d theta in here, this is d phi in here. Okay, and this one we're gonna apply the I think it's double angle or half angle formulas. I got cosine square theta is 1 plus cosine of 2 theta over 2. And this one I think is to have a formula in the back of the book. If not, then that's fine, I can do it. Sine phi times sine square phi. And then sine square is 1 minus cosine square phi. Phi. Keep writing theta. Okay? And then for the second part, you let u equal to cosine phi. And then du will be negative sine phi d phi. Alright? So this one right here, this is a u sub, then this is 1 minus u squared, and then negative du, and it's solvable. And this one right here, you're another u sub for cosine for 2 theta, you should have the answer. Okay, so let me stop the problem right here. The rest is going to be yours. Let me move on. And for a special case of the surface S. For the first example that I showed you was that the surface S is a sphere, right? So it failed the vertical line test. What if in a special case the surface S looked like this? This is my surface S. It passes the vertical line test. In other words, in this one we have the parametric equation of this one. This surface is going to be x, y, and then this cheese xy. Okay. Where z is equal to cheese xy. It is a function. Okay, z is a function of x and y surface. It passed the vertical line test. All right. Then it's the same idea, but this is going to be a little bit simpler. Actually, quite simpler than the general case. And you see, you have two variables for. Two parametric variables as well, but now we use x, y instead of u and v. So you calculate Rx, it's going to be what? 1, 0, dg over dx, right? And then Ry is going to be 0, 1, dg over dy. And you cross them, then you come back to our formula. And then Rx cross Ry will be x or y again. So for the I term is going to be 0 right here, minus dg over dx, comma, and then for the j term is what? Dg over dy times y with a negative, so negative dg and dz are the same. Okay, dy, and then for the last term, 1 minus 0 is 1. Okay. And you see something that you've seen before. The magnitude of this, Rx plus Ry, will be square root of dg over dx. I keep writing dz, it's the same thing as dg, okay, because z is the function g. dg over dx squared plus dg over dy squared plus 1. Okay. That's in case that you have a graph where the surface now passed the vertical line test. You have this. And the first example was the sphere, so it fails the vertical line test, but we can do it anyway. Okay. So the book shows you that if you have the special case of the function, so you can write it this way, double integral of f x y. Remember z now is what? The function g, right? Okay, and then times ds. What is ds now? ds dx dy, which is square root of dg over dx square dg is dz, the same thing. dg is over dy square plus 1 and then dA. dA is dx dy. Alright, just special formula. And if you have a function, say z equal to xy, then this should be more straightforward for you guys to get to the answer. Let me move on. Now I'm going to talk about the same thing, surface integral, but instead of the numerical value, we'll talk about vectors. Okay? How does the book called? Surface integrals of vector fields. Okay. Surface integrals of vector fields. Okay. So we define the surface integral of vector field like this: double integral over the surface S, capital S, vector field F times ds. Well, S here is what? The surface. We write it into a vector. Okay? It's gonna be equal to double integral over the region S. Right? Copy the same notation as above. Vector F times the unit normal vector n times ds. Now with the S right here, it's the same S right, but in terms of the area, not the vector anymore. And what do we mean by this? Let me try to explain it to you. Say you have a surface, okay? So it's the origin right here. This is S, okay? Alright. And any point on the surface, if you draw the normal vector, means a vector that perpendicular to the tangent plane. This is normal vector, okay? And we make it unit normal vector, okay? And F here is a vector field, okay? And ds now is what? The little area. This is ds, okay? And vector S is the origin. This is the y-axis. This is the z-axis. This is the x-axis. It's like R, but we use vector R for the line, the parametric equation of the line, so we use S here. Okay, it's like R UV. Okay. Two variable. Okay, and this is the definition. And let me unpack the package of this definition. You know that you have a surface S is R UV. Well, I think this is the same thing as a vector S. As we have right here. Okay? Let's go back to the way we write it. The book used S, but this is what it is, okay? S is RUV, which is X in terms of U and V, Y in terms of U and V, and then Z in terms of U and V. Okay? And then we know how to calculate the normal vector. First of all, we calculate RU, the tangent vector on the U direction, and then we're going to calculate RV, the tangent vector in terms of the V direction. And if we cross them, RU cross RV, we have a vector that's perpendicular to both RU and RV, right, which is the normal vector. So you want to make the unit normal vector, you take this cross product divided by the magnitude, RU cross RV. And this is the normal vector that we're talking about, the unit normal vector. RU is this way, RV is this way, and N is this way. Okay, perpendicular to both U and V. Okay. And the reason why we divide by this magnitude is to make this N got magnitude equal to 1. Okay. So, knowing this is my vector F right here. N is RU cross RV divided by the magnitude RU cross RV. And you know that ds is what? RU cross RV times dA. We learned that before, right? The little area on the surface is the little area of a parallelogram. Okay, so this can be simplified. So the definition of surface integral vector field F times ds can be translated to F dot, this one cancel out. Let me use the red marker. Right, this cancel out with this. Dot what? RU dot RV and then times dA. Okay. And dA now is du times dV. And this is the formulas you guys used to use to do the work. Okay. And again, one more time for this special case where your vector r, the surface vector r is x, y, and then g, x, y. Means what? You're having a function, okay? It may not be a sphere, it may not be. Anyway, this surface it passed the vertical line test. Then we calculated before RU cross RV was negative dg's over dx, comma negative dg. I write dz because it's the same. I usually write dz, but our book you g, so I'm gonna do the same thing as a book. And then 1. This is your u cross r. Okay, this is a 1 right here. And then f is just a vector field, so we defined it before this over region S. Okay, this is what? P Q R. Remember this notation for the vector f, vector field where P is a function of x, y, z, Q is another function, x, y, z, and R is another function, x, y, z. And then you dot what? Negative dg over dx, negative dg over dy, and then 1, and then dA. Okay, so how can you dot those two? So P times negative dg over dx minus Q dg over dy, and then plus R, and then everything dA. And this is another formula to help. Negative P dg over dx minus Q dg over dy plus R times dA. It means what? If you have a vector field F written down, and you know that the surface is a function, then you partial derivative of that function in terms of x, partial derivative of function in terms of y with a negative in front, okay? 1, and then you dot those two terms. And again, we're talking about vector F times RU RV. So it's help you to save some time of calculate the partial derivative first, partial derivative second variable, and then you cross product. Take some time. We do it for you. And then you plug it in. And again, dA here is what? Dx dy in this case. Because the u and v now is x and y. And I say I try to write dA in general because you may not use dx dy. If the region is like circular, then you're going to convert dx dy to polar coordinates, say RD, RD theta. Depends. Okay. And this is the end of 16.7. We was talking about the surface integral. So in general, surface integral, I introduced you guys 2 forms. The first one was in the functional form, the numerical value. You have a function f, right, low f, right, time